start. We have main engine start. 4, 3, 2, 1, 0, and liftoff. Liftoff of the space.
In our natural pursuit of knowledge, space has always mystified and beguiled us. Over the past 5 decades, we've pushed the final frontier inevitably onward into the ether. The cost has been colossal. Now every day, new data, new conclusions, and the thirst for deeper exploration propel us inexorably onward. The advantages of the discoveries made through space travel are myriad, but the fundamental curiosity as to what is out there will always fascinate and taunt us. Come with us now into the unknown and discover the disappearing frontier. In this edition, we look at the Voyager mission, exploring the mysteries of our neighbors in space and bringing us a greater understanding of the possibility of extraterrestrial life. We've come a long way since the Wright brothers and the flying machine prototypes of yesteryear. Always, the dreams of pioneers have seemed just that, reveries, pie in the sky. But throughout the past, we've been astounded, and the future promises to carry on that tradition. Jupiter. The first close-up portrait emerges. Late November 1973, 20 months after launch, Pioneer 10 closes in on Jupiter. Each hour brings the planet 20,000 miles closer. What lies below those inscrutable cloud tops? Could there be life in this maelstrom where pressures may reach 200,000 times Earth's? There were scientists who thought the answer might be yes. That deep in this raging atmosphere of ammonia, marsh gas and helium, the self-replicating spark may have been struck. In case the Voyagers encountered a cosmic neighbor along the way, the spacecraft carried sounds of the Earth, including the music of Bach, Beethoven and Mozart, the sound of a whale, of rain, heartbeats and laughter. They were permanently etched into the grooves of a special copper record, along with 115 photographs and diagrams depicting our civilization. One of these records was placed on each of the Voyager spacecraft before launch. The messages were designed to give a picture of 20th century Earth and its inhabitants to possible extraterrestrial civilizations who might intercept the spacecraft millions of years in the future. Venus was also thought to be able to sustain life. Once, scientists considered that because of the thick clouds, it seemed logical to suppose Venus to be a wet world, young, hot and covered with swamps. Result, it was imagined that only low forms of life existed there. Then in the 60s, spectrographic examination showed that if water existed on Venus, it was present only in trace amounts. The atmosphere, predominantly carbon dioxide and nitrogen. Conclusion, the clouds might be composed of fine dust. The surface could be an arid, windswept desert. The general feeling then was that the possibility of life on Jupiter and Venus didn't look too promising. However, our other neighbor, planet Mars, was thought to have conditions allowing life forms by both scientists and science fiction writers alike. Of all the other places that life might exist in the solar system, the chances appeared greatest that life may have at some time existed on Mars. And so a simulated expedition was developed on computer. After traveling through space for nearly 1 year, a unique landing craft approaches Mars to soft land on a planet covered with dust. In the Martian dust, there may be chemical evidence of life. In 1975, 2 Viking spacecraft were launched, each of which was programmed to land a robot on the Martian surface. One of its principal objectives was to test for the presence or absence of living organisms. A communication system linked the spacecraft to the mission control and computing center in Pasadena, California. On June the 19th, 1976, the first Viking arrived in the vicinity of Mars after a year-long journey of more than 400 million miles. Once in orbit, its cameras were turned to a detailed examination of the landing area. While the landers conducted experiments on the surface, the orbiters, swinging around the planet, measured variations in moisture and temperature and took high-resolution photographs of the Martian terrain. Over millions of years, the repeated flows of lava had built the volcanic mountains of Mars. 12 are larger than any on Earth. The largest, Olympus Mons, rises 3 times higher than Mount Everest and is broad enough to cover the whole chain of volcanoes that form the Hawaiian Islands. The great gash that cuts through Mars' equatorial zone is Varnis Marineris, a mighty canyon system that extends over an area more than 3,000 miles long and up to 400 miles wide and drops 4 miles below the flat, cratered surface of the plateau. The canyon walls are gullied, dissected by tributary canyons or scarred by catastrophic landslides, leaving steep cliffs and great fractured surfaces. Extending for 30 miles on the canyon floor is a field of sand dunes, suggesting that some of the debris produced by the collapse of the canyon walls was removed by wind. Because of Mars's low atmospheric pressure and low temperatures, water can't exist in liquid form. It must either freeze or evaporate. But while there are no oceans or rivers on Mars, there is more water in total than anyone had expected. The residual polar cap in the north, which remains after the hottest part of the northern summer, is water ice mixed with dust, and the measurements of the seasonal behavior of the water vapor over the planet suggest there is a vast reservoir of ice beneath the surface, so that one can think of the residual polar cap as the tip of an iceberg protruding from a sea of rock. At lower latitudes, a water vapor condenses to form clouds that ride high in the atmosphere or swirl around the slopes of Martian volcanoes. And further south, in the canyons and valleys, there is frequently an ice haze, seen to form and evaporate in the early hours of the morning as the sun warms the atmosphere. In this model, the flat surface of a large Martian plateau is cut by the Great Rift. A smooth, sloping ravine drops abruptly to the bottom of the canyon 4 miles below. The small peaks on the canyon floor were once part of the plateau's surface. Today, this great fracture in the crust of Mars is 75 miles across. The original fault has been widened and shaped by various forms of erosion. Great landslides are triggered by quakes that shake the crustal rocks. Wind-blown dust strips the canyon walls. Some side canyons have been deepened by running water. Melting of underground ice, followed by slumping of walls, further erodes the Great Fault. This Rift Valley, of which we've seen only a small part, is so huge that it would span the United States, and the Grand Canyon of Arizona would fit inside one of the smaller tributaries. These are just some of the mysteries of Mars, unlocked by the extraordinary Voyager missions. We've come a long way since the Wright brothers faced the dunes and the winds of Kitty Hawk with their first gliders. Montgomery and Linlithgow before them had shaped the wind, but they opened a new dimension to flight. The Wrights developed an aeroplane with the power of a gasoline engine. This gave the promise of a future in the air that had closed our world around us. And no two people are more than a day or two apart. The initial drive to perfect the aeroplane came because of its uses in World War I. Speed, range, and carry capacity increased, and by the end of the war, the aeroplane became a tactical weapon of importance. Within 7 years, the first regular airmail delivery was started between Washington, D.C. and New York City. And the first passenger service covered the 13 kilometers between St. Petersburg and Tampa in a flying boat. Aviation was soon pushing the limits of speed, altitude and distance. Glenn Curtiss and his R3C racer with pilot Cy Bennis, Al Williams and Jimmy Doolittle captured the speed record. In the 20s, the Atlantic was crossed many times, and in 1927, Lindbergh did it solo from New York to Paris. Willie Post and his Lockheed Vega and Winnie May set altitude records as well as circling the Earth. The Vega became a record breaker for many famous aviators. Jimmy Matten, Roscoe Turner, and Amelia Earhart. The National Advisory Committee for Aeronautics led in engine and aerodynamic research. Howard Hughes, a leader for 2 decades in aviation, set a new transcontinental record in his racer, as well as a faster time around the world in a Lockheed Electra. Lincoln Ellsworth made Arctic flights with Emerson in the airship Norga and explored the Antarctic in the Norfolk Gamma, an all-metal skin-stress plane. Admiral Richard Byrd had pioneered polar flights in 1929. In the 30s, the NACA developed a series of modifications that further improved the highly advanced radial engines of the time. Engine performance under the research of NACA's Lewis Center kept pushing aircraft faster and faster, and soon the flow of air over the wing's surface became a problem. They were called shock waves, forming around Mach 1. The efficiency of the wing was disturbed. One of the first aerodynamic fixes was the innovation of the swept wing that minimized shock wave formation. The B-47, one of the first military aircraft with the swept wing, had a control problem. At high speeds, the nose would pitch up. The solution turned out to be a simple device on the upper surface called a fence or vortex generator. James Osborne of the Boeing Company was the designer. When aeroplanes approached supersonic speeds, the problem of wind resistance became enormous. The solution was to remove volume from the plane's fuselage near the wings. This so-called Coke bottle fuselage greatly dissipated wind friction. The NACA research program developed the X-1, and on October the 14th, 1947, Chuck Yeager broke the sound barrier. The Douglas D-558 Phase 1 investigated high-speed flight with a straight wing. Then came the Norfolk X-4. and the D5-58 Phase 2 with a swept wing, flying at transonic and supersonic speeds. The Bell X5 provided research into wings which had a variable sweep, the Douglas X3. And then the X1A provided valuable research flights. The X2 worked at altitudes above 100,000 feet and beyond Mach 3. The X1E and the X1B continued the step-by-step research into higher Mach numbers and thinner air. The next step, the X-15, operated in air so thin that normal aerodynamic controls wouldn't work, and a new jet-powered guidance system had to be developed. The X-15 became the latest gold standard. It was built with the most powerful rocket engine ever installed in a plane and was propelled to speeds over 6,400 kilometers per hour and to altitudes in excess of 250,000 feet. The forces generated were so great that pilots had to undergo extensive conditioning in specialized flight simulators to avoid passing out. The experimental years with the now famous supersonic aircraft, the X-15, are considered by many the golden days of aeronautic achievement. It was a time of inspiring innovation, but also great danger. One flight with pilot Mackay at the controls had engine problems. An emergency landing on Mud Lake was ordered. The X-15's throttle was working at only 30%. It was too risky to keep the plane in the air any longer. Mackay survived the crash, but died years later as a result of the injuries he sustained. The aircraft was repaired in a matter of months. Peter Knight, Scott Fosfield, Robert White, Bob Rushworth, Bill Dana, Milt Thompson, Michael Adams, John Mackay, Joe Ingalls, Forrest Peterson, Joe Walker and Neil Armstrong. These were the X-15 pilots who flew in this joint program with the Navy, Air Force, NACA and NASA that set records for speed and altitude. Mach 6 and 107 kilometers up, they were the first men to go into near space. Bill Dana in the last flight of the X-15, 1969. In all, 199 flights were made over 9 years. In the 1970s, the competition to build the air fleets of the world challenged engineers everywhere. Increased air traffic, crowded airports, noise, pollution, and safety in the air were the problems faced. The B-70 was the result of research in NASA wind tunnels and laboratories, as well as the X-model aircraft. The B-70 was capable of supersonic speeds and was considered a prototype forerunner of the Concorde. But after a freak accident with another plane that caused the B-70 to crash, America's supersonic bomber and transport programs were cancelled. To the many engineers and designers of the time, it was a period of never-before-seen expansion, development, and most of all, creativity. With growing budgets and a public hungry for news of the latest achievements, organizations like NASA brought into existence any number of patentable inventions and innovations. NASA's wind tunnels saw many exciting experiments. Research into aircraft structure and safety were constant concerns for the wind tunnel team. They studied the phenomenon of flutter, a problem that can tear an aircraft apart, as well as researching stall spin, which has been with aviation since the beginning. In general aviation, the objective is to design an aircraft which will not enter into an inadvertent stall or spin. At NASA's Wallis Island Research Facility, aircraft were instrumented for spin testing. NASA pilot Jim Patton flew this particular test. About 30% of all general aviation fatalities can be traced to stall spin. On this research aircraft, when a recovery from spin couldn't be made fast enough for safety considerations, a parachute was deployed from the tail to aid recovery. At NASA's Langley Research Center, a series of controlled crash tests looked into aircraft structures. And here, a large helicopter fuselage was dropped from over 20 meters. Inside were anthropomorphic test dummies instrumented to record the factors which affect passenger survivability. The role of flow phenomena around an airfoil was studied by computer and in the wind tunnel. Of particular interest was the problem of vortex flow around the wingtips. This created turbulence in the air after large aircraft that resulted in dangerous conditions for following light aircraft. As a result, regulatory bodies have had to impose traffic delays in the landing and takeoff sequence behind jumbo jets. In order to give pilots a better organized cockpit and to provide instruments which are easily viewed, a system of head-up cockpit displays was developed. The aim was to aid pilots relying solely on their instruments during landings in heavy weather. The human factor and the conditions of communications in aircraft operation were studied extensively by NASA. Air traffic flow on and around airports was a concern. Air controllers had problems involving the relay of vital information to pilots and to controllers taking over a work shift. A system that provided for the reporting of unsafe conditions, violations of air traffic rules and other hazards to safety was instituted, and NASA, as the monitoring agency, received over 37,000 reports in its first 8 years. That brings us to the end of this edition. We look forward to your company next time. But remember, we are out there. What we can and can't see is out there, and the mysteries between us, although seemingly insurmountable, are encompassed by a disappearing frontier.